All right, here's a nice little example for relating power and stuff to each other. It's a good one. So we'll start with P equals IV. And you can see P equals IV. For t is less than 0, that's 0 times 0. So P of t equals 0. There we go. After that, it's a bit more involved. So P equals I. But if you want to be like serious about it, we're doing this in terms of t. So it's P of t equals I of t times V of t. So I of t here, actually we'll just go P of t equals 10 times e to the negative 5,000 t. Kilovolts is equal to 10 to the 3, so times 10 to the 3, and then volts, and then times that by 20 times e to the minus 5,000 t. All right, so that's all of it. So adding this all up, it's 200 equals 200k e to the minus 10k t. If you're wondering what I'm doing with like the k's and stuff, it just means I don't really want to write out all these zeros. So for every 3 zeros, I just put a k. So 200,000 just goes into 200k. Same with this, minus 5,000 t, minus 5,000 t, that's minus 10,000 t, minus 10k t. People say it like in real life as well, it's like $5k or whatever. Okay, so that's our equation. So at t equals 0.01, you just plug it in. P of 0.01 equals 200k e to the minus 10 times 0.001 t. Again, that's this one here, that means 10 to the negative 3, so that's 1 times 10 to the negative 3. I'm just telling you now, it's that. Actually, fuck, that should be 10k. That's the problem with sometimes you leave them out, but that's pretty good. That's so, sorry, not t. We've already times it by t, which we've made equal to 0.001. Yeah, cool. All right, and I can tell you that equals 9.08 watts. Now, the second part is more interesting because it made me actually discover how this calculus stuff works. So remember how we said that P is equal to dW dt? So we want to get W, which is energy, right? We want to get energy. Man, I spend like $12 on this fucking pen and it never works. Okay, dW dt. So W here equals energy. And we want to get W of t. And since this is all time dependent, like if you look at I and V, they're all time dependent. So we can't just, go joules per coulomb and then times it by coulombs per second to get joules per second. We have to do a full-on algebra thing. So we've already discovered that P of t is equal to 200k e to the minus 10k t. So sorry, this question wants us to get energy as a function of time, so W of t. Okay, so P of t equals 200k e to the minus 10k t. We've got up from here, and that is equal to dW dt. Now we're gonna do some algebra. So now dW equals 200k e to the minus 10k t dt. Integrate both sides. W equals 200k e to the minus 10k t dt, and we want to go from 0. Okay, so this is the tricky bit, right? So we want all this as a function of t. So when we integrate this with the variables, what we're going to get? We're going to get an antiderivative, and we're going to do it as in, bf of t, and then from t to 0, and that'll give us a function of t. But the problem is that if I do that just with this, because we want to get in terms of t up until t, the problem is that this is kind of messy because we've got t is here, it's part of this whole circuit, and then we're going to get t here. So it's like, well, is t the one we're differentiating, or is t the one we want an outcome? The truth is both. But so it's not messy, pretty much every mathematician will use a dummy variable instead. So it doesn't really change anything, but it just makes it more clearer. So we're going to go 200k e to the minus 10k x, and then dx. Let me see that. Yeah, okay, good. So it's a little bit confusing because we've just stuck x in there. It has nothing to do with like an x-axis on a graph or something. It's just a dummy variable. So we could put like, you know, theta there, or alpha there, or, you know, y, z, whatever you want. Just anything but t. So it's kind of confusing. What I like to do is I like to write this out so I know what I mean. And then I like to go down. Like technically, if you do this, it won't actually make a difference. It just might be confusing because you might get a different output. But yeah, so this is the proper way to do it. So I can tell you, I can just fucking tell you now. It's equal to, can I? Oh, maybe I can't. Whatever. You can evaluate that integral, and it's a pretty easy one to evaluate. And that'll give you w of t. But yeah, the point is, I just want to tell you how this dummy variable works. And then from there, if you want to get w, the energy expended over a certain point, so up until t equals 20. Because remember, energy is, it applies over a whole time period, right? So you can say, oh, I'm expending some energy per second. But that's actually what power is. If you're saying energy, you'd say, oh, the energy between t equals 0 and t equals 20. It's not instantaneous. You want a whole region of time where all this energy is being expended. It's like if you're running and someone's asking you while you're running, oh, how much energy are you using? And you're like, well, what do you mean? How much energy per second? How much energy have I used so far? So what this is saying is how much energy so far. But if we want energy per second, that'd be power, and that's fine. We just plug it into this. But yeah, so energy is a concrete thing. It has nothing to do with time. Whereas power is all about time. Yep, all right.